Arthur, you can go ahead and introduce Tom.
Okay, welcome everybody to today's meeting of the online CUNY set theory seminar. And we're very pleased to have Tom Benhamou to speak to us today. He's coming to us from Tel Aviv University, and he will be talking to us about intermediate Prikry-type models, quotients, and the Galvin property. Okay, take it away, Tom.
Okay, thank you very much for having me. It's a pleasure. I just have to say that I work under the supervision of Professor Moti Gittik. So this entire work is a joint work with him. Okay, so let me, oh, why doesn't it work? Okay, let me outline the talk, the two talks actually. So we start with some background, we'll give some background about the problem we're trying to tackle. Then we will introduce the forcing in subject. This is the first, we have two forcing in subjects. So the first one will be the Megiddo-Radin forcing. We will present the main result. Then we will sketch most parts of the proofs, of the proof. And then we will elaborate on the last part of the proof, which involves the Galvin property and how it relates to quotients of the Megiddo-Radin forcing and generally to Prikry-type forcing. And if we'll have time, then probably next time we'll speak about the Prikry forcing. Okay, so we'll probably end this talk somewhere in the middle of 2. This is our goal. Okay, of course, if there's any questions, you can feel free to stop me at any time. I'll be delighted to answer any question. So let's start with some background. So consider the following two well-known results about intermediate models. The first is that any intermediate model of a Cohen generic extension is a Cohen generic extension. The second one is that any intermediate model of a random real generic extension is a random real generic extension. This phenomena of structure of intermediate models holds also for Prikry forcing, the standard Prikry forcing, and this result is due to Gittik, Kopke, and Canove. They proved it in 2010. Actually, what they prove is that for every normal measure over kappa U, and every V generic filter V for the Prikry forcing with U, producing a Prikry sequence CG, and for every set in the generic extension, there is a subsequence, a subset or a subsequence C of the generic sequence CG, which produces the same model, such that the model generated by A is equal to the model generated by C. I hope that this notion V square bracket A makes sense to you. Basically, you can think about it as the minimal ZFC model, which includes V and as A as a member of it. There are a formal way to define this model inside a given generic extension VG. Even without a generic extension VG, we can define the Z union of L square brackets with some things. I would not want to get into how this model is defined, but unless someone would like me to elaborate on this. Okay, so let me explain how from this theorem we can conclude what are the intermediate models of the Prikry forcing. So this is a corollary. So in the setting of the last theorem, take any M which is intermediate to the ground model V in the generic extension VG, a ZFC model definable in VG, then M is also a generic extension for V generic filter G prime of the same Prikry forcing. Okay, and the proof is quite short. So every such model is of the form VA for some set A in the generic extension. This is a well-known fact. By the previous theorem, theorem 2, it follows that M is of the form V of C for some subsequent C of the Prikry sequence. And by the Matthias criteria, since we assume that M does not equal V, then this subsequent C cannot be finite. So C is an infinite subsequence of the Prikry sequence, so it's itself a Prikry sequence. So So this is a Prikry generic extension. Okay, the goal of this talk is to investigate the structure of other Prikry-type forcings. The first one would be the Megiddo-Radin forcing, and the next one is the tree-Prikry forcing. Let us describe the question we would like to address more accurately. So the question subject is, what forcings P have a generic extension which are intermediate to a generic extension by the Megiddo-Radin forcing or by the tree-Prikry forcing? When we will get to the tree-Prikry forcing, we'll see that this is a matter of consistency as well. So there would be several forcing which there will not always be intermediate to the tree-Prikry forcing. Okay, let us now present Megiddo-Radin forcing. So Menachem Megiddo introduced this forcing as it's a generalization of Prikry forcing, but the goal of this forcing was to find a forcing which preserves cardinals and change the cofinality of some measurable cardinal kappa to have uncountable cofinality. And this is done by adding a club of low order type to kappa. We will present this forcing formally later. There is another forcing which relates to the Megiddo forcing. This is the Radin forcing. It also adds a club with similar properties to the Megiddo club, but it has the property that it can keep kappa regular or even measurable. Nowadays, there are several variations of Megiddo and Megiddo-Radin forcing which are used, and we will describe formally the one which we are going to deal with. So, for example, Fuchs used the Megiddo's original variation for Megiddo forcing to prove the following maximality result. He proved that for any two Megiddo generic sequences C and D over a ground model V, if D belongs to the model generated by C, then D must also be almost included in C. So beside finitely many points in D, all the other points should be in C. Okay, how does this relate to intermediate models? It relates in the following sense. So two Megiddo generic extension can be intermediate to one another only when one is almost included in the one generic club is almost included in the other generic club. This is what this theorem says. Okay. Are there any questions so far? Okay. Well, let me just make two notational remarks. Yeah. The first is that I'm not going to distinguish between sets and the sequence, which is the natural increasing enumeration of the set. Okay. So I'm talking about sets of ordinals. So I will go back and forth from the set and the sequence. The second notational remark is that we force in the Israeli style, meaning that Q is above P in the order means that Q provides more information, that it is stronger. Namely that Q forces that P is in the generic. Okay. Let us present now the forcing notion, the Megiddo forcing version that we are working with. So, we follow the Megiddo forcing description from the handbook, the Prikry-type forcing chapter, which is originally due to Mitchell. We fix a coherent sequence U. I wrote here the definition of coherent sequence. I would not really want to get into it because basically it's hidden in the facts I'm going to give about Megiddo forcing later. So we won't really need the definition itself for a coherent sequence. I'll just give it for the completeness of the talk. So you guys have it. So it's here. So this is the definition of a coherent sequence. A coherent sequence is a sequence U which is indexed by pairs of which domain is pairs of ordinals, alpha and beta. So alpha is this is the measurable, and beta would be the index of the measure. So each U alpha beta is a normal measure over alpha. the number of measures you have over a given alpha is the order of alpha. We denote it by the order of alpha. And what does the coherency mean? The coherency means that whenever you take an ultra power with one of the measures, so let J be the elementary embedding, which is induced by when taking the ultra power with the normal measure U alpha beta, then the requirement is that when we restrict J of U to alpha, so when we take the image of U, we get a coherent sequence by elementarity, and when we restrict it to alpha, to the same alpha we took the ultra power with, we get U restricted to the pair alpha beta, where what does it mean to take a coherent sequence and restrict it to an ordinal? It means simply take all the measures up to this ordinal alpha, including alpha himself. Okay, so, and what does it mean to restrict a coherent sequence to a pair? So take all the measures up to alpha, not including alpha, and on alpha itself, we only take the measures up to this beta, which is provided here. So we erase, we keep all the measures on alpha, which have index below beta. So the idea of a coherent sequence that this enables us to reflect measure on a certain measurable cardinal to ordinals below it, to measurable cardinals below it, using this coherency. Okay, this is I think the major advantage of working with coherent sequences. Okay, let me go back to. Okay, so we fix a coherent sequence U, and let us define the Megiddo forcing with this sequence of this coherent sequence. The conditions of the forcing, which I denote by MU, are of the finite sequence of pairs. Each pair consists of an ordinal and a set, such that. Second, yeah. So the ordinals form an increasing sequence below kappa. Always the largest, the ordinal in the most right pair would be kappa. The kappa is the maximal measurable in the sequence U. So the ordinals form an increasing sequence below kappa, which is intended to approximate the final club. And the sets AI are, as usual, sets of candidates for the continuation of the sequence. So we have two possibilities. Either we have some ordinal alpha I, which has order 0 in the coherent sequence, namely it does not have any measures inside this sequence, in which case the set of candidates is empty. We do not allow to extend below this in the interval of this ordinal and alpha I minus 1, or it is measurable in the sequence U, so it has order higher than 0, in which case the set of candidates should be of measure 1 with respect to all the measures provided on this alpha I. Okay, so how is the order defined? So I wrote here the formal definition of the order, which I'm not thinking it's quite clear how it works. So let me just show you how to think about it. For this, I need to go back to my writing page. So let's say we have a condition here, P in MU. And let's say we would like to extend it somehow. So there are three ways we can extend it. Either we shrink all the measure 1 set we have on the all the measure 1 sets. So some of them can be empty, so they will stay empty. And then this way we can form the so-called direct extension of P by just not adding any pair and simply shrinking all the measure 1 sets. So each VI would be a subset of AI. This is the first possibility. The second option is to perform one-step extensions by picking some ordinal beta in some AI. So you fix any I, so you have the set of candidates AI, you pick a candidate beta from the set of candidates. And then there are two options for this candidate. Either it is of order 0 with respect to the coherent sequence. So we would like to add the pair beta empty set to the sequence. And we do it basically between alpha I minus 1 and alpha I. And the only thing we need is to make sure that the set of candidates now starts above this, beta we added. So we cut AI above beta. We denote this by beta and then I don't know, concatenated, P concatenated with beta. Okay, so this is in case that the order of beta is 0. In case that the order of beta is larger than 0, then we add a pair of the form beta and AI intersection beta. So we take all the, we are already committed to candidates from the set AI. So when we add an ordinal beta, we are still committed to the same set of candidates. So we cut the set of candidates at beta. And then we would like to add, oh, this is a typo here. Not a typo because I can erase it. This is AI intersection beta. This one should be here. And of course, if you would like it to be a legitimate condition in MU, we must require then this set is of measure 1 with respect to all the measures on beta now. So we can only choose candidates from the set of candidates on which the set AI reflect, in the sense that when you cut a set of candidates with beta, you get something which is in the intersection on all the measure 1 set you have on beta. We can always make sure that given a measure 1 set, we can shrink the set of candidates such that every point is a reflection point. This is not just a technical thing. Okay, so and we will assume that every work in this dense subset of MU that every beta in there has in the set of candidates it's a reflection point of this large set AI. Okay, so this so a general sorry.
Tom, so that basically means you can forget about case 2b.
No, why?
I thought. I mean, didn't you just say you can work below a condition in which every point reflects in that sense? Yeah.
Yeah. So I can just forget about this requirement.
Yeah. Sorry, I meant you can forget about case 2a.
No, because you are allowed to add points of order 0. The only thing this enables you can always pick a point of order 0 or point of order greater than 0, whatever you like. But this observation I made can only make sure that that you don't have to worry that if you pick a point, then the set does not reflect. You can pick any point you want, no matter what its order is. You can pick it, and it's a reflection point.
I see. Okay. All right. Thank you.
Okay, let us go back to the. Okay. So this is a general extension is performing this one-step extension and this direct extension finitely many times. This is a general extension. Okay, so in other words, so when does P is direct extension of Q? When we have exactly the same pairs. So the ordinals of the pair, we just shrink the measure 1 sets. This is what I just said.
I have a question also, Tom. I think I missed
Sure.
something in the definition. Why do we need to cut down AI?
Because it should be why do we need to do it? Because we would like to have a set of candidates. Let me go back to the
Yeah, I think I missed something in the definition.
Sure. So the point of this, when you add this pair here, beta AI intersection beta, this means you're adding beta to the generic club, and now you would like to see what set is responsive. You would like to provide a set of candidates for the continuation of the sequence, but in the interval alpha I minus 1 and beta.
Oh, okay.
So when you intersect, you must intersect it with beta to get a set of candidates in this interval. Okay, does it make sense?
No, I mean, why do you need to do AI minus beta plus 1?
Oh, because here now this set will provide candidates in this interval, which is ordinals between beta and alpha I.
Okay, I see.
Yeah. So AI would be a subset of the interval beta and alpha I.
Okay, perfect.
So no, not AI. Sorry, AI minus beta plus 1. Sorry, this is a mistake.
Okay, I got it. Thank you.
Yeah, sure. Okay. Any other questions? Okay. Let me go back. Okay. So let us state some facts about Megiddo forcing, which I'm not going to prove. You can find them either in the handbook or you can go to our paper, which is in the reference at the end. And just let me remark that the difference of this variation of Megiddo forcing and the original variation of Megiddo forcing is that in the original variation of Megiddo forcing, you have to have a system of functions which tell you how measures on higher cardinal and measurable cardinals reflect to measures on lower measurable cardinals. Where here, the coherent sequence already takes care of it for you. So you don't have to specify how measures reflect onto lower measures. Okay. Which I think makes it a bit, it hides out some difficulties in the general variation of Megiddo forcing. Some facts about MU. So let us fix some V-generic filter G for MU. So first, let us describe the club added by this sequence. So it's basically all the ordinals which appear in some pair of a condition in the generic extension. So you collect all the ordinals of pairs which are inside conditions which are in the generic extensions. Okay. It forms a club in Kappa, and the order type of this club is either Kappa, in case that the order of Kappa is above at least Kappa, or it is of order type omega to the order of Kappa, where here the power is power of ordinals. So we will see in the next slide examples where the order of Kappa is, for example, 2, then the order type of CG would be omega squared in the sense of ordinal. Okay, so this is the first fact. The second fact is how can we identify successor ordinals of CG, where if you pick a point of CG of the generic club, then it would be a successor if and only if its order is 0. And the reason is that the set of candidates, if you take any condition P which has alpha as an ordinal of one of its pairs, so the set of candidates we provide on alpha is empty. So you cannot add anything in the interval alpha and the predecessor pair in P for this alpha. Okay, so it would be successor eventually in CG. You cannot continue the sequence in the interval. MU satisfies Kappa plus CC because Kappa is measurable in the ground model, and there are Kappa many possibilities for the pairs below Kappa. So the alpha 1 to alpha n with the large set, this is all of size Kappa. And any two conditions which have the same lower part are necessarily compatible because we can just shrink the sets we have on Kappa itself. And MU satisfies the Prikry condition, which says basically that any formula sigma in the forcing language and for any condition P in MU, you can directly extend P, so without adding any ordinals, just shrink the measure 1 sets, such that the direct extension decides the statement sigma. Okay, you can always, so generally you can always extend P to a condition which decides sigma. This is general thing about forcing, but here you can actually do it with a direct extension. This is the advantage. Okay. So this is condition 3. And now condition 4, basically this is a kind of a Matthias criteria for Megiddo generic sequences. But this is one direction of it, which we're going to use. So if delta is any limit point of CG, and A is any set which is measure 1 with respect to all the measures provided on delta in this coherent sequence U, then the generic club CG up to delta must eventually enter this measure 1 set A. Okay, so if you have a set A, which is of measure 1 with respect to all the measures of a limit point delta of CG, then CG up to delta must enter this measure 1 set from a certain point. This is a generalization of the Prikry Mathias criteria we have in the Prikry case. That just simply that the Prikry sequence enters any measure 1 set from a certain point. Okay. So the next point, the next fact is that when given a U measurable lambda, there is a natural way to factor the forcing above a condition which has lambda as one of the ordinals in the pair. What do I mean by U measurable lambda? Simply that the order of lambda is larger than 0 in the coherent sequence. So given any condition P in MU for which lambda is one of the measurables appearing in P, we can factor P to 2 parts. Simply take all the pairs where the ordinals are below lambda, the pair where lambda appears, including lambda itself. This would give you a condition in forcing I denote by MU intersection restriction to lambda. It's basically a Megidor forcing up to lambda. Okay, it produces a Megidor sequence up to lambda. And then the second part is just the pairs of ordinals above lambda. And this belongs to a Megidor forcing in the interval lambda kappa. So it produces a Megidor sequence in the interval lambda kappa. And in this sense, MU projects factors into 2 parts. Okay. Note that the first part is of cardinality 2 to the lambda, because these are pairs where the maximal pair is lambda, and there are subsets of lambda there, so it's at most 2 to the lambda. And the upper part has a high closure degree. How less or equal star closure degree? How I is the closure degree of less or equal star in the upper part, where it is above 2 to the lambda, certainly, because the closure degree corresponds to the completeness of the measures you have on the upper part. And over there, the first measurable would be a measurable above lambda, because how it's defined. So you have a high less or equal star closure degree. Okay. This is another property. So take any A which is a subset of V alpha. So it's not written here. This is a typo. A is a set in the generic extension. It is a set in VG, which is a subset of V alpha. V alpha is the regular V alpha, but from the ground. So, so for example, you can think about a subset, a set of ordinals, which is a subset of the ordinal alpha. Then A must belong to V CG intersection lambda. It must be added by the part of the forcing below lambda. Where what is lambda? Lambda is the last limit point which is less or equal than alpha. The last limit point of CG which is less or equal than alpha. And this exactly exploits 5. Let us maybe prove sketch a very short proof for this. This will make sense. So, okay. So now we have this set A, which is a member of the generic extension VG, and it is a subset of V alpha. And we consider now, so this would be a generic extension for the forcing MU restriction to lambda. And the forcing which completes this model to VG is the forcing MU restriction to lambda kappa. Well, you can ask yourself, okay, maybe I need to generate the coherent sequence for the measure here because I added subsets to measurables here. But actually, we don't really have to. We can simply take the one from the same definition from the ground model and force with it over this model to obtain a model, to obtain this model. Apparently, this is the same. Okay. So we force with this forcing to complete this model to this model. And let A be a name in the upper part forcing for this set A. And let us take a condition which forces that this A is a subset of V alpha. So forces in the sense of this force, of the upper forcing. And now we can do the following. For every beta in this VA, we can use the Prikry condition to find a direct extension of this P. We call this direct extension P beta. So it has the same ordinals as P. We only shrink the large sets in P beta, such that P beta already decide the statement beta belong to the name A. Okay, and we do it for every beta separately. We find the direct extension. Now, since the cardinality of V alpha, so since this set has cardinality which is strictly less than the closure degree of less or equal star of this model, so this model, the first measurable, is much above the cardinality of V alpha. We assume here that lambda is the last limit point which is less or equal than alpha, which means that the next measurable is going to be strictly above alpha. This is less or equal, but this is strictly less. This is the definition of lambda. So we are guaranteed to find a single P star which is above all these P alphas together. This is for every beta. Okay, and therefore this P star already decides A, because A is forced to be a subset of V alpha, and for each beta in V alpha, we decided the statement beta belongs to A. So P star already decides A, and since we can do it densely. Often, then we can pick such a condition P star in the generic, which actually tells you what this A should be, and therefore A can be or must already belong to the model VCG intersection lambda. Okay, so this is how we. Is this okay? Okay, I hope it's okay. If I'm going too fast or anything, please let me know, because I'm not sure. Can you guys hear me?
Yes, we can hear you fine.
Okay.
Could I just ask you a quick question? It was just when you split the forcing in the lower part and the upper part, say at lambda or something like that, is it sort of to split it below a condition which has lambda in its domain? Or
Yeah,
that's
exactly.
Right?
Yeah, you have to split it below it. So you force in Israeli style. So above a condition which has a lambda in it. Yeah.
Right. Yes. Okay.
Okay. Thank you for this remark. Okay. Okay. So another fact is that MU, of course, preserves cardinals and changes cofinalities. We spoke about it. And which are the ordinals that MU change cofinality to? So the first observation is that if alpha is some V regular cardinal which changes cofinality in the generic extension, then it must be a limit point of CG. This is also a result of this factorization. Let's see, it's a very short proof to see that if alpha change cofinality in the generic extension, then it must be a limit point of CG. So why is that? Well, suppose that lambda is suppose that alpha is strictly below two limit points of CG. So this situation, let's show that alpha cannot change cofinality. And the reason is that the forcing up to lambda, so lambda is a limit point of a CG. So there must be a condition which has lambda as one of its ordinal P, such that for some A, this pairs appears in P. and P is a member of G. And above this condition P, we can split the forcing up to lambda and above lambda. So up to lambda, we have a Megiddo forcing up to lambda, which, as we said, is lambda plus CC. And since it's lambda plus CC, it does not change the cofinality of things above lambda plus. So this lower part keeps it does not change the cofinality of lambda. But then the upper part has does not, as we said earlier, it does not add new subsets to VCG intersection lambda. So it must also keep, it cannot add a new cofinal sequence to alpha because it does not add bounded subsets below this lambda prime. So it must also change, preserve the cofinality of alpha. Okay, so in this situation, it must be that the cofinality of VG of alpha is the same as the V cofinality of alpha. Okay, the lower part is lambda plus C, and the upper part is sufficiently close to not less or equal star close to not add bounded subsets to subsets to alpha. Okay. Okay. So these are the only points which can change cofinality are limit points of CG. Now, which of the limit points of CG change cofinality? Where there are two kinds of limit points of CG. They are necessarily the order is above zero because of point 2. Point 2 says that the successor point of CG are order 0. So limit point of CG are of order larger than 0. So there are two possibilities. Either the cofinality of this order is below alpha plus, so the V cofinality of this order is below alpha plus, in which case the cofinality of VG of alpha is below alpha. So kappa alpha changes cofinality. And the second option is that the cofinality of the order of alpha is at least alpha plus, in which case alpha stays regular. So the point that change cofinality in VG are exactly the limit points of CG, for which the cofinality of the order of alpha is below alpha plus. This is a characterization of the points which change cofinality in the generic extension. Okay, these are 10 points which we need for this talk. These are the facts we need about Megiddo forcing. Okay, any questions so far before I present the main result and some examples? Okay, so some examples of intermediate models of the Megiddo forcing. It is quite easy to see that the Megiddo that an intermediate of Megiddo forcing doesn't have to be a Megiddo generic extension. So we rule out the possibilities for the Gitti-Canove and Kopke generalization straight away, because say for example the order of kappa is 2. This means that kappa carries two measures in the coherent sequence U kappa 0 and U kappa 1. Generically, what will happen is that we will add a Prikry sequence to U kappa 1, to the measure U kappa 1. And by the coherency, each Prikry point from the measure U kappa 1 would have order 1 in the coherent sequence. In this sense, the measure reflects. So if you pick a point which is typically corresponds to the measure U kappa 1, then it would be of order 1. So what does it mean it is of order 1? If you have a Prikry point of order 1, it has a large set associated to it of the order 0 of this Prikry point. So it will produce its own omega sequence. So maybe let me just show you another picture. So we have kappa, and we produce a Prikry sequence to kappa for the measure U kappa 1. And one of the large set in U kappa 1 is the set of all alpha less to kappa, such that the order of alpha is 1. This is a measure 1 set with respect to U kappa 1. This is by coherency. So by the Matthias criteria, this will eventually enter this set, this measure 1 set. So all the points here will eventually have order 1. What does this mean that they have order 1? It means that in the conditions which they belong to, we're trying to, we have a set of candidates, and now they are responsible to create their own Prikry sequences. So here we will create a Prikry sequence for U kappa 1, 0. Here we will create a sequence for U kappa 0, 0. So here we'll have another omega sequence, and kappa 2 will have another omega sequence. And if we glue together omega sequence of omega sequences, then we get something of order type omega square. Okay, so this is how we get something of order type which is more than omega. And now, for example, if the order of kappa is going to be 3, then we will have a Prikry sequence for the measure U kappa 2. Each Prikry point for the measure U kappa 2 will typically have an order 2, and therefore it will produce, as in this situation, something of order type omega square. And when we glue together omega sequences of order type omega square, we get something of order type omega to cube. I think this is omega to the power of 3. Yeah. And we see that in general we have this omega to the order of kappa. This is going to be the order type of the generic club. So indeed, we have in the case that the order of kappa is 2, then the OTP of CG is omega square, and we denote by CG to CG we enumerated CG of I less than omega square. And now, so if you take simply the omega first elements of this thing, this is going to be a Prikry sequence for the first Prikry point of the measure U kappa 1. So for CG of omega, this is going to be simply a Prikry extension, a simple Prikry extension. So it's necessarily not a Megiddo generic extension. Okay, so this is a
sorry,
example.
Tom, could I just ask? So it's not Megiddo generic for the same system of ultrafilters, but is so, and Prikry forcing is also cannot be viewed as a special case of this,
Yeah,
or
it
is
can.
it?
It
can
can
be, right? Yeah. So it's
sure.
still. So it would still
Megiddo
there would still be a
type,
chance
yeah.
that everything is like a Megiddo type. So you don't have a counterexample to that, at least, yeah. Okay.
I do, but
not yet. I mean,
yeah, it's example 7, 8, 9. But yeah, it is a Prikry type, so it's Megiddo type. I agree.
Right.
And we will have something. We will need to define formally what Megiddo type is, because this is not just this type. Let's consider the next example. Okay. Okay. So assume that the order of kappa now is omega. This means that we produce a sequence of order type omega to the omega. Now we can consider the omega sequence where we plug in the indices omega to the n to the Prikry sequence. Oh, sorry. Yeah. Now by the previous example, this means that every point CG omega to n, it produces something of order type omega to the n below it. So it must be of order n, which means it is a typical point from the ultrafilter U kappa n, from the measure U kappa n. And these are different n's. For every n, this is a different n. So we pick one point from each measure. So it is basically a diagonal Prikry sequence for the sequence of measure U kappa n, where you typically pick one point from each set which corresponds to an ultrafilter. So this is quite different from the previous example, but it is still Prikry type. This is important to note. So we simply now we can think maybe we should simply specify which measure to pick each point from, and then this would give you all the possible intermediate models. But no, there are still complications for that. Let's consider the next example. So suppose now that the order of kappa is delta
Tom,
0.
Tom,
Yeah, sure.
can I just interrupt you? You're still showing the image where you write. We can't see what you're currently reading. Yeah, maybe you should switch.
Yeah, sorry. So now is it okay?
Yeah.
Let me go well in this example, because if you didn't see it. So again, I have, and now if the order of kappa is omega, then the order type of CG is going to be omega to the omega, and we consider the intermediate model where you simply plug to CG the point omega to the n. Okay, and as I just said by the previous example, you can now simply each point CG omega to the n produces something of order type omega to the n. So it must be something of order n, which is a typical point from the measure u kappa n. So each point in this sequence comes from a different measure. So these are different n's. So this sequence, this omega sequence CG omega to the n less than omega, is a diagonal Prikry generic extension with respect to the sequence of measures u kappa n less than omega. So as I said, we still have the conjecture that you can maybe somehow specify certain measures and then pick one point. It's still the conjecture now should be something like a diagonal version of Megiddo forcing, which we simply prescribe which measure we would like to pick points from. Okay, so the next example is going to be a bit more complicated. So assume that the order of kappa is delta 0, and the order of delta 0 is 1. So the order of kappa is some u measurable cardinal of order 1. Okay? So the order of kappa is 1. This is the shortest way to say it. Then we can pick a generic, we can find a generic extension. So since the order of kappa is delta 0, then the order type of the Megiddo club would be omega to the delta 0, and since delta 0 is measurable, it's simply delta 0, right? Because ordinal power omega to the delta 0 is delta 0. And the omega-ist element of this sequence would be delta 0 itself. Okay, so I can do it because the order of delta 0 is 1. So if I consider a pair of the form, let's consider a pair of the form delta 0 and A, and I don't know, some kappa and B. And if you have a generic with this condition in it, then since the order of delta 0 is 1, it would produce a Prikry sequence below delta 0. And naturally, we will have that the order of kappa is delta 0. So this is how you get this situation. Okay. Just this. And now, okay, so we created a Prikry sequence for delta 0, CG of n and less than omega. And we now, since the order of CG of alpha is delta 0, we can now plug these Prikry points to CG. So we can create now the sequence CG of n. So it will look like this. You have delta 0. You can see what I'm writing right now?
Mm-hmm.
Okay. So you created a Prikry sequence. So it's CG of 0, CG of 1, etc. This is an omega sequence, and you go up to kappa. Here you have something of order type delta 0. So you can plug in these points. So you have CG of 0, then CG of 1, and so on. This will actually witness the fact that that the cofinality of kappa in the generic extension is omega. Okay. So this is the next example. Then this sequence, what forcing generates this sequence? Well, it also must be something diagonal because these points typically have order. So CG of n will have order. Now, typically CG of n. So it must be a Prikry point from the measure u kappa CG of n. So naturally, it would be a diagonal Prikry sequence for this sequence, because this is the order of each of these guys. This is the order of each of these guys. But now, how does it differ from the previous example?
The sequence of measures is not in V.
Exactly. So the sequence of measure I is not in V. So what kind of extension is it? It's a two-step iteration. The first step would be Prikry forcing on CG omega. And the second part would be a diagonal Prikry forcing with the indices which are the Prikry sequence from the first part. Okay. So these are two different things. Okay, let's continue to the next example. The final example, we assume that the order of kappa is kappa, and that this is a very important example, and therefore the order type of CG would be kappa. So why is the order? How do we see that kappa changes cofinality in VG, although the order of CG is kappa? The point is that if you consider the set of all alphas less than kappa, which have order less than themselves, so the order of alpha is less than alpha, then this would be a measure one set with respect to all the measures on kappa. This is the coherency. This means that the CG will enter this measure one set from a certain point. So every point of CG would be every point of CG would be it would have order less than itself from a certain point. Okay. So it cannot produce something. So if you look at CG up to this point, it would not produce something of the same order type. So each alpha from CG, which comes from this set, cannot produce something of order type alpha. So it means that the first closure point of this enumeration of CG would be kappa itself. So how do you construct now an omega sequence in kappa? You simply take alpha 0. Say all the points on CG enters this set. Okay, for simplicity. So let alpha 0 be the first element of CG. Alpha 1 would be CG of alpha 0, alpha 2 CG of alpha 1, and so on. Then when you take the soup of these, you should reach a closure point of the enumeration. This is basically how you get any closure point in any sequence. But this point now cannot be bounded in kappa because what we just said. So it must be unbounded in kappa. Okay, and let us ask what kind of forcing generates this thing. Well, there is a Matthias criteria for the Prikry forcing I proved, and you can simply see that this sequence satisfies the the Matthias criteria for Prikry forcing for the sequence of measures U kappa alpha. Okay, so it's a Prikry generic extension. I hope this was clear. Okay. Clearly, all these examples are Prikry-type forcings. So we should have a conjecture about that all the intermediate models are Prikry-type forcing. Let's see now the main result. So this is the theorem by Moti and me. Let U be a coherent sequence with a maximal measurable kappa, such that the order of kappa is less than kappa plus. Okay, so this is a quite restrictive assumption about the order. So, for example, we do not consider the case where kappa stays regular or measurable. We're formulating this result by induction. So assume that for every delta less than kappa, in every coherent sequence W with a maximal measurable delta, and any set A in the generic extension for some generic filter H for MW, there is a subsequence C of CH such that the model generated by H is the same the model generated by C. So this is an inductive assumption that the Gittica-Novey-Kopke result holds for ordinals below kappa. Then what we prove is the inductive step for order kappa less than kappa plus. Then in this case, for every V generic filter G, in any set A in the generic extension by this G, there is a subsequence C of the generic clubs, such that the model generated by A is the same as the model generated by this subsequence. Okay, so if we prove this inductive step, we can now say that to obtain the first step towards the classification, that given any V generic filter producing a G which produces a Megiddo sequence CG, such that now here comes the part of the induction. For every alpha in CG, the order of alpha is less than alpha plus. Then for every set in the generic extension VA, there is a subsequence C of the generic club such that the model generated by A is the same as the model generated by C. Okay? So this is exactly, this is a generation of a Gitty-Kopke and Canovese result, but for a Megiddo forcing with O alpha less than alpha plus. And now recall what we did for Gitty-Kopke and Canovese result. We used the Matthias criteria to see what the intermediate models are. However, in this case, as we've seen from the previous 4 examples, these was all subsequences of the generic club, and it is not quite clear what models of the form VC, what forcing generates this VC. Okay, so I hope I convince you that it is not clear what VC is. So as we've seen from the example, we are not sure what VC is, and in 3, what we did, we restrict even more the order of kappa to be less than kappa, and we defined so-called Megiddo type forcing, which is what I said earlier. You simply have 2 functions which tells you from which measure you should pick the point from. This is denoted by MFU. And we proved that any such extension VC is a finite iteration of such forcings. Okay, so this is a classification, finite iterations of Megiddo type forcing. If we'll have time, we'll prove this classification, but the main part is to prove theorem 10. Okay, is the theorem what we're trying to prove clear? You would want me to go over it again?
I think it's very clear.
Okay, great. Okay. Okay, let's sketch some of the main ideas from the proof of 10. So basically, we reduce to sets of ordinals. So here in the theorem, we have a general set A in the generic extension, and I would like to reduce to sets of ordinals. This proposition says, okay, you can reduce to set of ordinals. And I would like to skip this proposition because the proof is quite easy and it's standard. So if it's in the slides, you can see it later. So let us assume that A is indeed a set of ordinals, and let us prove the theorem by induction on the sup of A. So we have an inductive hypothesis in the theorem about the last measurable appearing in the coherent sequence, but we're inside. Now we're doing it by induction on the supremum of the set of ordinals, so which we denote by lambda. In the first case is when lambda is below kappa. Kappa is the last measure. And this case follows from the following lemma. So suppose A is a subset of V. For example, if A is a set of ordinals, then this is the case, such that A is in the generic extension. The cardinality of A is less than kappa. So if the sup of A is less than kappa, then clearly the cardinality of A is less than kappa. Then there is a C subset of then the theorem follows. So there is a subsequence of the generic sequence such that the model generated by A is the same as the model generated by C. Great. So this is our first goal, to prove this lemma. And for this, we need the strong Prikry property for this variation of Megiddo forcing, which I'm not going to prove. I'm going to state it, but I'm not going to prove it. So in order to explain what the strong Prikry property is, I need the following definition. So a tree T of finite sequences, increasing sequences below kappa, is called a U-fat tree if it is a tree of finite height. And every knotted in tree T in T, either the set of its immediate successors is of measure 1 with respect to some measure of U, which appears in U, or T is a maximal branch, or there are no continuation to T in the tree. We denote the set of elements of the set of maximal elements, the set of maximal branches by MB of T, so maximal branches of T. Okay. So what is the strong Prikry property? So basically, okay, so if a tree you split on some measure 1 set in which appears in U. This is this old definition. So what is the strong Prikry property? So suppose you have a condition P in MU and a dense open subset of MU. Then there is a direct extension P star of P and a U-fat tree T, such that for every maximal branch B in maximal branches of T, when we concatenate B to P star, we enter D. Okay, so given a condition and a dense open subset, we can find a U-fat tree such that any extension from a maximal branch of the tree enters D. This is the strong Prikry property. Okay, so now we need some, the last thing we need before we prove lemma 12 is some combinatorial property of U-fat trees, which I think is a nice observation. I won't prove it here, but you can find the proof also in 4. So let T be a U-fat tree, and suppose that F is a function defined on the maximal branches of this U-fat tree to any set B. Then there is a U-fat tree T prime, a subtree of T of the same height, and a set of levels I is a subset of the levels 1 to height of T, such that for any two maximal branches of T prime, the restriction of T and T prime to I is equal if and only if the function, the value of the function on these T's is the same. So this is a generalization of a well-known result of ultrafilters. So we know that given a function on a large set A of a normal, such that A belongs to a normal ultrafilter U, you can always restrict it to a measure 1 set such that the restricted function is either constant or 1-to-1. This is a well-known combinatorial property of a measurable, of a single normal measure. How is this a generalization? So when you consider now functions which do not take a single ordinal, but take a finite sequence of ordinals, of course, you can contradict this by simply, I don't know, taking the projection on a, so f of alpha beta is alpha. So this is, you cannot hope that this would be constant or 1-to-1. It depends, but it does depend in a 1-to-1 way only on the first coordinate. And so you can eliminate the coordinate beta and simply keep the coordinate alpha. So this lemma says that you can, any such function, you can always restrict the U-fat tree to a smaller, to a sub U-fat tree with the same height, such that, and find the important coordinates, so the levels of the trees, which are exactly the one which are, with respect to them, the function is 1-to-1, and the function does not depend on the coordinates which are outside of I. This is what this if and only if says. Okay, so this is the combinatorial property I'm going to use. And now let us prove lemma 12. So that if A is, so the theorem for sets of cardinality less than kappa. Okay, so suppose that, for example, that A is countable. I think that in order to avoid technicalities, this would be much clearer. The general case is, of course, it won't be exactly the same, but this is the major idea. I think it would be clear from this case. And let us fix a sequence of names, of MU names for this set A. We call it tilde AN, n less than omega. Now let us start with the density argument. So fix any condition P in MU. And for each n, we apply the strong Prikry property to the dense open set of conditions above P which decide the value of this name AN. This clearly is a dense open subset of MU. So by the strong Prikry property, we can find a direct extension Pn of P and a U-fat tree Tn such that any maximal branch from that tree, when we concatenate it to Pn, we decide the value of An. Namely, there is a ordinal gamma such that Pn concatenated with beta forces that an equals gamma. Okay. Now this defines a function on the maximal branches of Tn. So now this denote the function fn of beta to be this decided value gamma. So we apply the combinatorical, the previous combinatorical lemma to shrink this tree Tn to T star n and find some important levels In for this function. Okay, so by the lesser equal star closure, we have only omega many direct extension of P. We can find a single P omega, which is star above all the Pn's. And this is some black box now I'm giving you guys, which is not very hard to show that now we can directly extend this P omega such that the set of the set P star concatenated with T, where T is a maximal branch of T star n, forms a predense set above P star. This is some fact. Okay. So by density, let us pick such a P star in the generic G. And this, and since we ensure that the set P star concatenated with T, where T is a maximal branch of T star n, is predense above P star, we can find a maximal branch Dn such that P star concatenated with Dn belongs to the generic G. So we in the generic we have this sequence of branches Dn. Which one of them decides the value? And since the value as interpreted in G is the real value, it means that the function, when I plug in this maximal branch, gives me the correct value, An. So this means that from this sequence of branches, I can use the function fn to get the value An. But now we see why we needed these important coordinates, because from the value An's, I cannot necessarily reconstruct the branches Dn because there might be many Dn's which give me the same value. And this is why I needed to restrict to the important coordinates. So now we define C to be the union of all the Dn restriction to In. So In is the set of important coordinates. We only keep the important coordinates from all these branches. And we claim that DC works, namely that VA equals VC. Okay, so let us prove first that A belongs to the model VC. And this is not very hard. So in VC, we have the sequence of Dn restriction to In. We can reconstruct all this Dn restriction to In, only the important coordinates. By the axiom of choice, we can find branches D prime n in the maximal branches of T star n, such that the restriction is the same as Dn restriction In. So we know that there exists such Dn, but when we need to define this inside the model VC, we don't know exactly what we get. And therefore, but as long as the Dn prime and Dn agrees on the important coordinates, we are ensured that Fn of D prime n and Fn gives us the same value, which is An. So the set A can be defined the set of Fn, D prime n less than omega, and this is definable in VC. As for the other direction, so in VA, we can calculate Dn restriction to In by taking for every n, take D prime n be any branch to be in the pre-images of An. Okay, and now we know that D prime n and Dn gives us the same value, and therefore they must agree on the important coordinates. And we conclude that we can define C inside the model VA by taking the union of all the D prime n restriction to In. So this gives us the equality VA equals VC. And we're done here with this with this first part of the induction. Now we can derive some other combinatorial properties of the club using this observation about trees. So we have the following lemma, which again I'm not going to prove here, but it's which I think of it as an Hausdorff-like separation property. I mean a topological separation property, and I will explain my intuition after I'll phrase the lemma. So let delta be any limit point of CG. And let Y be a set in the generic extension, a set of ordinals, such that the cardinality of Y is less than delta. Okay? And suppose that this set Y is disjoint to CG. Then there is a measure one set X with respect to all the measures provided on delta, which is also disjoint to Y. Okay, so why do I think of it as a separation property? Because, okay, so basically we know that CG enters this set X from a certain point. This is the Matthias criterion. And so X is thought to be somehow thicker than G. And when we have this set Y, we say, okay, we have this set Y, which is of cardinality less than delta, where delta is some limit point of CG, and Y is disjoint to this thinner set CG. Then actually we can thicken CG to X and still stay disjoint to Y. Okay, so no topology. You have a point, you have a closed set. You can find a closed set which concludes which includes this point and is still disjoint, right? So this is my intuition. So as a consequence, we obtain a force result for this variation of Megiddo-Radzin forcing. Given two generic filters G and G prime for MU, such that G prime is in VG, then the CG prime minus CG is finite. So CG prime is almost included in CG. In particular, if we have equality of the models, then the symmetric difference is finite. Okay, let us see how does it follow from lemma 15. Sketch the proof here somewhere. Okay, where is it? Okay, to write it. So we have suppose otherwise. We have CG prime minus CG would be at least omega. So let us consider let delta n less than omega be the first omega many elements of this difference of CG prime minus CG. Okay, and let delta be the supremum of this delta n's. This delta is clearly delta is a limit point of CG, so it is measurable in the ground model. Clearly, its cofinality now became omega. So delta, so the cofinality Vg of delta is below delta, which means that by our observation, the delta is also a limit point of CG. This must be the case because it changed cofinality in CG. Okay, now we apply the Hausdorff separation property. We have this set Y, which is the delta n's n less than omega. This is, since it was chosen in the difference, Y intersection CG is disjoint, and clearly the cardinality of Y is less than omega, is less than delta. It's omega, so it's less than delta. So therefore we can thicken CG and we can find some X. So there is, by the lemma, there is some X in the intersection on all the measures provided on delta, which stay disjoint to Y. But this is, of course, impossible because CG, these points comes from CG, and CG is a Megiddo generic sequence. So there must be, on the other end, there must be some delta prime below delta, such that CG prime intersection with delta prime and delta is included in X. But this is impossible because Y is a subset of CG prime. Okay, so this is a contradiction. I hope this is clear. Let me see. I'm not gonna do. Okay, I'm just gonna say that for subset of Kappa, we won't prove it here. It's a very technical thing. And I think that next time we will start with the assumption that we proved it for subsets of Kappa, and we will do the induction step for sets A, which have supremum at least Kappa plus. Okay, or is this okay? Can we stop here, or would you like me to continue?
Sounds good. It's good timing. Yeah.
Okay.
I think it makes sense.
Are there any questions? If it was again too fast or
No, it was great. It was great.
Yeah.
Perfect speed. Yeah,
Okay.
I love it when I can follow things.
Yeah, it was fantastic.
Yeah,
Okay.
Very
very
clear.
good.
Thank you. Thank you.
There was one question that just occurred to me, and it's probably silly, but and I think you could ask the same question about the original Megador forcing. So maybe probably it's a naive question, but so you always work with systems U that have a maximal coordinate. So what would happen if they had, I mean, if the domain of the U sequence were just a limit? I mean, with a maximum missing.
So the forcing would start by picking a maximal measurable and then forcing over it, right? So
yeah, but
unless,
it would be, you would never have this definite ending, right? I mean, so you would pick a coordinate, but above it, you would still have many options.
do you allow, so I'm not sure what now is the definition of the forcing. Do you allow to extend above the maximal pair? So
otherwise it would be boring. Yeah, right.
Yeah,
I
okay,
mean, yeah,
okay.
yeah.
Yeah. Yes, so you take, okay, so you, I'm not sure. Well, I'm not sure what will happen because you somehow, the limit point, so you take the limit of these measurables in the domain. So it's called this kappa. If it is not measurable, so say it is of cofinality omega, I'm not sure how properties of this measurable reflects downward. Yeah, it's an interesting question. I'm not sure.
Okay.
But even in Megiddo's original formulation, he fixes kappa.
Right. Yeah.
Didn't think about this forcing before, like without. Let me think about it. Maybe a good answer next week.
Yeah. Okay.
Any other questions? Okay. Thank you very much, guys.
Thank you.
See you next week.
Thank you very much.
Thank you.
Bye-bye.
Bye-bye.
See everyone next week.